One of the things that we've been interested in a lot over the past few years is this issue of prediction. And I'll give a couple of examples from infectious disease. So we might want to make predictions about where the next influenza is going to come from. This is a map of H5N1 bird flu in domesticated or wild bird populations. We also, as scientists, use prediction every day. And some people would consider, in fact, prediction to be in itself the scientific method when we think about cross-validation. So we may have 3 different models here that we fit to the blue time series, and we might compete them on a held-out set in red, and we would maybe pick the model at the bottom because it performed the best on this held-out set. But it turns out from infectious disease, we're actually, for the most part, not so good at predicting. There are some examples of us doing a very good job, but there are a lot of examples of us not doing such a great job. This is a prediction from the CDC. 2 months after the Ebola outbreak started, they thought there was going to be 100,000 cases, and there were only 10,000 cases. So they are off by a factor of 10 at their prediction. So the question that Giovanni Petri and I have been trying to ask is, can we predict outbreaks? Or, as I mentioned in my title, can we predict these complex adaptive systems, these human, social, socio-technical, socio-biological systems? And maybe a way to think about it is, can we predict this influenza time series? And one of the things that we want to avoid doing is arguing about whether we have the right model for predicting, whether we have the right metric. Do we care about the root mean squared error? Do we care about the mean absolute error? Do we care about the log likelihood? So we're going to adopt a metric called the permutation entropy, which is a model-independent metric of time series predictability. It tells us how good we should expect to be able to do at forecasting a time series. It works in 2 dimensions pretty simply. So if I want to predict a time series of 0, 1s, I count up how many times I see 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, and I build a distribution over these. And the flatness of this distribution of the Shannon entropy is the permutation entropy, and 1 minus that is the predictability. So high entropy, low predictability. In 3 dimensions, we could just calculate different motifs after we discretize them. So this is what it looks like for a white noise time series and a sine wave time series as we see more and more data. So white noise, very high entropy, low predictability. Sine wave, very low entropy. It's highly predictable, but importantly, it's stable. So let's do this exercise. Let's play this Bayesian learning game where I'll start seeing more and more and more data. I'll see longer and longer and longer time series. And I'll ask what happens to the predictability, what happens to the permutation entropy. All right, so here's what we have for noise and sine wave. No change, it's flat. So let's think in our heads for a second what we might expect to see with this infectious disease time series. Bayesian theory tells us as we see more data, we should become more certain of the truth. So the entropy should go down. We see the opposite. The entropy rapidly climbs as we go through one flu season and then spikes at about the level of white noise. As we see more data, we become increasingly less certain about the reality. You might wonder, this is just influenza in Texas. Maybe Texas is weird. Texas is weird, but it's not influenza in Texas. Each dot is a time series from another state in the US. The length of the time series is on the x-axis. The permutation entropy is on the y-axis. For all of these time series in all 50 states for influenza, as we see more data, we become less certain about the truth. Our ability to predict goes down. And you might wonder, maybe this is just influenza. Influenza is notoriously hard to predict. It's a little bit strange. It's not just influenza. This is time series length for US state-level data as a function of permutation entropy for chlamydia, dengue, gonorrhea, hep A, influenza, measles, mumps, polio, and whooping cough. For all of these diseases, as we see more data, we become increasingly less certain about the reality. I'll very quickly end by saying it turns out we can predict the entropy rate gain based on the number of secondary infections, so a biological property, the growth rate of the pathogen. And we can predict as well based on the social contact patterns that the disease is spreading over, which is why we think this is a general phenomenon and not just related to disease. If you tell me the network over which information is transmitting and how that information is lost, we can tell you how long you're going to be able to forecast. Thanks.